and chapter 15 about algorithm design techniques. Algorithm design techniques. Techniques used to design algorithms. In real life, when we are asked to do some work, we correlate it with our experience and then try to solve it. In real life, when we are asked to do some work, we try to correlate it with our experience and then try to solve it. We link it to something we already know from our past, from our experience. Then we try to solve it. Similarly, when we get a new problem to solve, we first try to find the similarity of the current problem with some problems for which we already know the solution. Then solve the current problem and get our desired result. Similarly, when we get a new problem to solve, you as a developer, as a programmer, have a new challenge, someone asks you to do something. We first try to find the similarity of the current problem with some problems for which we already know the solution. Many times the developer or the programmer search the GitHub and try to find the code written for it, right? Then solve the current problem to get our desired result. This method provides the following benefits. It provides a template for solving a wide range of problems, to provide the idea of the suitable data structure for the problem. It helps us in analyzing space and time complexity of algorithms. So we will get the template, we will get the data structure, and we'll get the space, which is the storage time, which is the time required to accomplish something, complexity of algorithms. In the previous chapters, we have used various algorithms to solve different kinds of problems. In this chapter, we will read about various techniques of solving algorithmic problems. Again, in the previous chapters, we have used various algorithms to solve different kinds of problems. With so many algorithms, many ways of solving things. In this chapter, we will read about various techniques of solving algorithmic problems. Now, the algorithm itself might have a limitation or problem or weakness. We will see the techniques of solving that. Various algorithm design techniques are brute force, greedy algorithms, divide and conquer, decrease and conquer algorithm or technique, dynamic programming technique, reduction, transform and conquer, and backtracking and branch and bound. Right? So these are techniques used in designing algorithms. 6 different techniques. We will talk about each single one now. Brute force algorithm. Brute force is a straightforward approach of solving problem based on problem statement. It is one of the easiest approaches to solve a particular problem. It is useful for solving small size data set problems. And many of the C++ examples in the beginner level depends on this. Some examples of brute force algorithms are bubble sort, selection sort, sequential search in an array, computing power a to the power of n by multiplying a n times, multiplying a by itself n times, convex hull problem, string matching, exhaustive search such as traveling salesman, knapsack, and assignment problems. That was the first technique. The second one is the greedy. We talked about 6, right? And we said we are going to cover them. We talked, this is the brute force, this one is going to be studied next, and then we'll talk about these 4 later on. All right? One by one. We finished the first. Now we are talking about the second, called the greedy. In the greedy algorithm, solution is constructed through a sequence of steps. At each step, choice is made, which is locally optimal. Greedy algorithms are generally used to solve optimization problems. Where do we use a greedy algorithm in solving optimization problems? Why? Because we are always looking for the optimal. We always take the next data to be processed depending upon the data set which we have already processed, then choose the next optimum data to be processed. Greedy algorithm does not always give optimum solution. Yes, it's greedy, but does not provide the best solution always. Does not always give optimum solution. Some examples of brute force algorithms are, it's not brute force, it's greedy. All right. Some examples of the greedy algorithms are minimal spanning tree, like Prim's algorithm, Kruskal's algorithm, Dijkstra's algorithm for single source shortest path problem, optimal result, right? A greedy algorithm for knapsack problem, the coin exchange problem, Huffman trees for optimal encoding. All right. So we talked about the second one. The third algorithm design technique is divide and conquer, or sometimes they call it decrease and conquer. Decrease and conquer, occupy, or divide and conquer and occupy. Divide and conquer algorithms involve basic 3 steps. First, split the problem into several smaller sub-problems. Second, solve each sub-problem. Then finally, combine sub-problem results. Combine the results so as to produce the final result. So make the big problem into smaller problems and try to solve each single one, then put them all together again. In divide and conquer, the size of the problem is reduced by a factor, half, a third, etc. While in decrease and conquer, the size of the problem is reduced by a constant. Examples, so this is the difference between decrease and conquer versus divide and conquer, okay? In these 2 lines. All right, examples of divide and conquer, and we have examples, and examples of decrease and conquer, and we have the below examples. Let's see the divide and conquer. We first divide, then we start solving each single piece, then combine the result. These are the 3 steps, right? Merge sort algorithms. Merge sort algorithm using recursion. Quick sort algorithm using recursion. Computing the length of the longest path in a binary tree using recursion. Computing Fibonacci numbers using recursion. And a quick hull. All right, this is the divide and conquer. What are the examples of the decrease and conquer algorithms? Computing the power a to the power of n, right? by calculating a to the power of half n using recursion. All right. Binary search in a sorted array. Binary search in a sorted array. Decrease and conquer. Searching in binary search tree. Insertion sort. Graph traversal algorithms, DFS and BFS. Topological sort. Warshall's algorithm using recursion, permutation, minimal change approach, Johnson-Trotter algorithm. Computing a median, computing a topological storing and fake coin problem, which is a ternary search. Consider the problem of exponentiation. Compute this. So if we try to compute this using a brute force, it requires n-1 multiplications. Divide and conquer, it requires n-1. Decrease by 1, it requires n-1. Decrease by constant factor, it requires n. Or the constant minus 1 times n. All right. Dynamic programming. Right. The next one is the next algorithm design technique is dynamic programming. While solving problems using divide and conquer method, there may be a case when recursively sub-problems can result in the same computation being performed multiple times. This problem arises when there are identical sub-problems arise repeatedly in a recursion. Dynamic programming is used to avoid the requirement of repeated calculations of the same sub-problem. So if we have some part that's repeating, we use dynamic programming. In dynamic programming, we usually store the result of the sub-problem in a table and refer to that table to find if we have already calculated the solution of the sub-problems before calculating it again. So we just check, see if we already done this. This is dynamic, right? Dynamic programming is a bottom-up technique in which the smaller sub-problems are solved first, then the result of these are used, here's a typo again, to find the solution of the larger sub-problems. All right. Examples: the Fibonacci number computed by iterations, Warshall's algorithm for transitive closure implemented by iterations, Floyd's algorithm for all pairs shortest path. And here's the Fibonacci by iterations. So it calls itself. And we can do the same with the factorial, right? We'll make it call itself. And this, we have to watch the stack memory because a stack overflow can happen. And right. And here's the Fibo and the comment underneath it. The next algorithm design technique is reduction, transform, and conquer. These methods works as two-stage procedure. Two stages. The first, the problem is transformed into a non-problem for which we know optimal solution. So we transform it to something we know. And the second, the problem is solved. Right? The most common types of transformation are sort of an array. The most common type. For example, given an array of numbers, find the two closest number. The brute force solution for this problem will take distance between each element in an array. Will try to keep the minimum distance pair. This approach will have a time complexity of n squared because each one will be compared to the full thing. So it's like square the total number. This is the time complexity, right? Transform and conquer solution. We first sort the array in n log n, time, then find the closest numbers by scanning the array in linear form, which will give the total time complexity of n log n. Example: Gaussian elimination and heap sort. This is the example. Backtracking in real life. Let us suppose someone gave you a lock with a number, 3-digit lock, number range from 1 to 9, and you don't have the exact password key for the lock. You need to test each and every combination till you get the right one. Obviously, you need to test starting from something like 111, then 112, and so on, and you will get your key before you reach 999. So what you are doing is backtracking. This is what is meant by backtracking. You test every single possibility. And if it's 3, then you start from all ones and you change one at a time until you cover all the possibilities. Suppose the lock procedure, the lock produces some sound or a click. Correct digit is selected for any level. If we can listen to this sound, such intelligent heuristic will help you to reach your goal much faster. If you have a click, then you can search much faster because you just scroll them fast and it will click, right? These functions are called pruning function or bounding functions, the click thing. Backtracking is a method by which solution is found by exhaustively searching through large but finite number of states with some pruning or bounding function which will narrow down our search for all the problems like NP hard problems for which there does not exist any other method. We use backtracking. If we don't have any other method, we use this backtracking way. Backtracking problems have the following components: initial state, target or goal state, intermediate states. Of course, we have the initial, the target, and the intermediate. The path from the initial state to the target goal state. Yes, we do have that. Operators to get one state to another. And pruning function that stops the thing. The solving process of backtracking algorithm starts with the construction of the state tree, whose nodes represent the state. The root node is the initial state, and one for more leaf node will be our target state. Each edge of the tree represents some operation. The solution is obtained by searching the tree until a target state is found. Backtracking uses depth-first search. What do we use? We store the initial state in a stack. While the stack is not empty, repeat. Read a node from the stack. While there is available operators to do, apply operator to generate a child. If the child is the goal state, return the solution. If a no state and pruning function does not discard it, push the child into the stack. All right. And here we have problems that uses the same, right? And we'll just move forward. And branch and bound. And branch and bound algorithm design technique. Branch and bound method is used when we can evaluate the cost of visiting each node by utility function. At each step, we choose the node with the lowest cost to proceed further. Branch and bound algorithms are implemented using a priority queue. Branch and bound algorithms are implemented using a priority queue. In branch and bound, we traverse the nodes in a breadth-first manner. A-star algorithm. A-star is a sort of an elaboration on branch and bound. So it's related to the previous topic, branch and bound. All right. In a branch and bound, at each iteration, we expand the shortest path that we have found so far. In A-star, instead of just picking the path with the shortest length so far, we pick the path with the shortest estimated total length from start to goal, where the total length is estimated as the length of the traverse so far plus a heuristic estimation of the remaining distance from the goal. Branch, so it's an elaboration on the branch and bound, the A-star. Okay, branch and bound will always find an optimal solution, which is shortest path. A-star will always find an optimal solution if the heuristic is correct. Choosing a good heuristic is the most important part of A-star algorithm. Conclusion. Usually, a given problem can be solved using a number of methods. However, it's not wise to settle for the first method that comes in our mind. Some methods result in a much more efficient solutions than other. For example, Fibonacci number calculated recursively decrease and concur approach and computed by iteration dynamic programming. In the first case, the time complexity is 2 to the power of n, and the other case is just n, right? Another example, consider sorting based on insertion sort and basic bubble sort. For almost sorted files, insertion sort will give almost linear complexity, while bubble sorting algorithm have a quadratic complexity. So the insertion sort is faster. So the most important question is how to choose the best method. First, you should understand the problem statement. Second, by knowing various problems and their solutions. And we are done with chapter 15, and we'll stop the video here, and in the next chapter we'll talk about the brute force algorithm. All right. See, we finished 465 pages out of 585, so we have less than 100 pages. We are approaching to the end of the book. We'll see you in the next video.